they're rattling around. And because they're rattling around, as you squeeze them down, they sort of hit more often and push you back out. It turns out, if you look at the physics of it, it's exactly what's happening in a bicycle tire. Where there, it's the air atoms rattling around. As you squeeze them down more, they're pushing back out more.
Air pressure.
So it's like air pressure. It just happens to be with light hitting on the atoms because it's stuck. It's exactly the same thing that holds our sun up and keeps it from collapsing farther. Is what they call like photon pressure.
Oh, okay.
So yeah, there's certain things called core collapse supernova, where the core stops producing light, and the star implodes because there's nothing holding it up anymore.
It gets cold.
Yeah.
So with more observations,
Yeah.
say at finer resolution with smaller differences in temperature, is that going to make more peaks, or are you just going to be able to extend that out a little farther with higher resolution images?
Higher resolution images, smaller dots will make it this way. Higher precision images are what make the error bars small. So WMAP sort of already did that. If I'd shown you this picture 4 years ago, these error bars are like that, and they went down, but they didn't have real small pixels. So in fact, this is the last one they did. These are actually running on their experiments. So they didn't actually go down below something of more than about 0.3 of a degree. So the finest angular resolution. So, all right. Well, let's go on, and let's look at this. I don't know. I'm not an optical astronomer. I love this picture. There's a good story, which probably most of you know better than I do, but this is a career-threatening move, this picture. The reason, so if you think about sort of the cost per hour of the Hubble, it's high. And there's the whole politics of how you divvy up the time and committees and all of that. But one of the things they do is they give the director a couple of weeks worth of time, with the idea that things are sort of high risk or a little bit off, they can't get time otherwise. He can parcel it out. And the way it's normally done is, he'll give out a few hundred of these little observations and see what happens. But the director said, I'm going to take those 2 weeks and let's find a spot on the star charts where there is nothing. Just absolutely blank. And let's stare with the Hubble for 2 weeks. Now, if you take 2 weeks of Hubble time and don't get any picture back, your career is over. But he did that, and it's actually not this picture. It's the precursor of this one, which is slightly smaller. You get a picture like that. The field of view is about the size of a pencil eraser held at arm's distance.
Half a degree? Tenth of a degree.
Yes, I'm trying to remember. It's been, I even say in my notes, I don't. It's all under half a degree. I forget what it is.
Yeah, it was very small.
Size of the moon, or a lot smaller than the moon?
Than the size of the moon. I don't remember. That's embarrassing. I'm not an optical astronomer. There are 10,000 galaxies in this picture. And I just love the feeling of, take that pencil eraser.
Billions and billions.
Billions and billions, yeah, exactly. So, but I can imagine looking at how galaxies clump, too. If we imagine there was this early gas with certain areas that were denser or not dense, we'd expect the galaxies not to be uniformly distributed either. Now, there's a trick here, because just because two galaxies look pretty close together here does not mean that they really are, because one may be a lot closer than the other. So much pain and suffering. You go through, you do all your spectra, you look at your lines, and you find out your redshift, and you do that for a few million galaxies, and you get pictures like this, which were two large stripes done. This is a 2D field survey, and where each dot is a galaxy. And you see these areas which are very dense and very dense. And if you go through and actually look at, well, what are the sizes of the clumps of galaxies, you get another power spectrum. Little bumps and rings, and it's actually probing to line this up with the other map, it would be further down in the little low resolution in that you can't see from the scene. So anyway, that's all fun. Those are sort of some of the tools that we do. But let me move back. I want to talk about this new emerging area of cosmology called the Epoch of Reionization, and some of the work that we've been doing recently. So, going back to this picture, the question that we started out with was, how did we get from smooth to clumping? And the way that you'd like to answer that question is to go look at these first galaxies, stars, quasars, as they lit up. That turns out to be extraordinarily hard, though, observation. You can't build just a bigger telescope to do it. So to talk about why this is hard to do with optical telescopes, let me tell you the story of hydrogen. So if I lay this over, hydrogen makes up the majority of the atoms in our universe, and it comes in two forms. There's neutral hydrogen, where you have a proton and an electron. The electron is going around. And there's ionized hydrogen, where they're floating independently. And you can go from one to the other, and that an electron will hook onto a proton in a high orbital state and jump down through the little orbits to get down to the ground state. And a high-energy UV or X-ray photon can come along and hit that electron and kick it off. So you can go back and forth between them. So what we started out with early, before the cosmic microwave background, is a plasma, which means that the electrons and the protons are floating free. But it was very dense. The universe was very small. But there was a lot of light rattling around. So every time an electron tried to hook on to a proton, it was immediately kicked off. But the universe continues to expand and cool, getting farther and farther apart. And what happens at the cosmic microwave background is that the electrons all of a sudden have time to hook on and jump down into that lowest state before they're hit by a photon. And so all of a sudden, everybody combines up. And the universe goes from fully ionized to fully neutral. And it's that transition which releases the cosmic microwave background light, allows it to travel.
Is that the recombination phase?
Yes. Yeah, that's exactly what it is. So now we have a very smooth universe, and it continues to expand and cool. But the little density areas start collecting gas together, and you then eventually get the first galaxies which light up over here. But there's one important thing to remember about neutral hydrogen, which is that it is very opaque to ultraviolet light. Ultraviolet light absorbs amazingly well. Now, why do we care about that? Because this is at such a high redshift that what we see as optical light here started out as ultraviolet light here before it was redshifted. And so what we would see with an optical telescope is absorbed immediately out here. It never gets to us. But one answer is, well, let's look at what's optical light here. That's low enough in frequency that it can get through the neutral hydrogen. But what's optical here has dropped so low in frequency by the time it gets to the Earth, it's deep in the infrared and absorbed by our atmosphere. So we're sort of stuck. We want to see these things. How do we do it? Well, one answer is to build the James Webb Space Telescope. And this is one of the primary things it's designed to do. You put it up above the atmosphere and you build something and look deep in the infrared. But the other way turns out to be that the hydrogen itself, this gas between the galaxies, glows in radio.